Hi guys, today we'll talk about quantum tunneling. It is a very important phenomenon in quantum physics. As we all know, in classical physics, if a particle wants to climb a very high mountain, it must have enough kinetic energy to overcome its potential energy at the top of this mountain. Otherwise, it will fall back naturally, and it will never appear at the other side of this mountain. However, things can be quite different in the microscopic world. Imagine a very small particle meeting a potential barrier. Even if it doesn't have enough kinetic energy to cross this barrier, there is still a finite probability of finding this particle at the other side of the mountain, meaning that somehow it magically crossed this barrier. How could this even happen? The main reason rests in the essential difference between the classical physics and the quantum physics. In quantum physics, particles are not regarded as solid, but instead it has wave-particle duality. Therefore, we use wave function to represent its motion instead of the classical motion equation.
So I'm going to introduce what is a wave function and what it actually represents. So firstly, by definition, wave function is just a mathematical description of the quantum state. And it's quite similar to the position or acceleration, etc. in classical mechanics. And also, we say that the particles are inherently probabilistic. And this term means that they could appear in a range of positions instead of being at a certain point. So for instance, in classical physics, I can represent the position of an object as x equals to something. But in quantum physics, I will just represent this position as a probability of it appearing between 2 points. And just notice that the wave function varies with both position and time. But in this case, it's just an example for better understanding.
So in order to calculate the probability of a particle appearing in a certain range of positions, we take an absolute value there, and then we square that, so that we can get a probability density function for the particles appearing. And this whole equation is just the basic assumption of quantum physics. Firstly, we need to normalize the equation since the particles have to appear somewhere. So this must equal to 1. And by calculating this equation there, we could get a value, and we need to divide this number to the whole equation and makes that equals to 1. So if I get a 3, I need to divide this 3 to there and to make the result equals to 1. And then we just use the second equation to calculate the area under the graph, which is probability of appearing between A and B.
So we can describe the wave function by using this equation here, the time-independent Schrödinger equation. The important terms to note here are psi, the wave function of the particle, E, the energy of the particle, and V, the potential that the particle is in. Here we have some solutions to the Schrödinger equation. For the case where V equals 0, we end up with a sinusoidal wave function. And for the case where V equals U0 and the energy of the particle is less than U0, we end up with a decaying wave function or a negative exponential. If we have a free particle approaching a potential, we end up with a combination of the previous solutions, where here there is no potential and the wave function is sinusoidal, and then inside the potential, the wave function decays exponentially. If the potential barrier is narrow enough, then the wave function will not have fully decayed by the time it reaches the end of the potential. And then here, where there is no potential again, the wave function will be sinusoidal again. Now we know that the probability of finding a particle is described by the modulus squared of the wave function. So this means there is a small chance of finding the particle on this side of the potential, despite the particle having less energy than the potential. This is quantum tunneling. Here we have an animation of this happening. We have a wave packet approaching a narrow potential barrier, and a small part of the wave packet tunneling through the potential.
So, in short, quantum tunneling is the ability of an electron to pass through a potential barrier. But how is this helpful? Well, quantum tunneling enabled researchers to develop a scanning tunneling microscope, an instrument so precise that it can create images on the scale of atoms. The tip of the microscope, a sharp metal needle, is brought really close to the surface to sense the position of the individual atoms. Then, an electric voltage is applied to create a tunneling current. This will make the electrons tunnel from the surface to the tip. We will then need to drag the tip across the entire surface while maintaining a constant voltage to complete the scan. This means that the tip will move up and down following the contours of the surface. It is extremely important as it allows researchers to create a 3D profile of a surface. Another important application of quantum tunneling is nuclear fusion. The hydrogen nuclei in the sun's core, being positively charged, repel each other. In order for them to fuse and release heat, they must overcome the repulsion in between them. But they don't have enough energy to do so. This is when quantum tunneling comes in place. It gives them the chance to fuse by passing through the barrier between them. This is what makes the sun the star we can see today and the one that we will see for a long time.